Good morning, folks. This is Todd Coburn of Cal Poly Pomona with the Aerospace Structures series. This is Aero 3261's Lecture 16a, which corresponds with shearing stresses and beams. This is a very important topic because in this you're going to learn a number of things. First, you'll be able to figure out how to find the shearing stress anywhere in a cross section. Now, back in Lecture 3, I believe it was, we learned that the shearing stress, we learned how to calculate the shearing stress, but we assumed that it was constant across the section. It was just P over A. Now, that's not really true. That does happen to be close to true if we have a thin-walled member like an I-beam. But when we have any kind of structure with significant area other than the extremes from the, if it's not super thin, then it will tend to, what we'll get is a parabolic distribution of stress. Actually, there's always a parabolic distribution of shear stress, but sometimes the change in shear stress is so slight in that parabola that we can assume that it's P over A with not a huge loss of accuracy. Today we're going to be looking into the more accurate formula that looks at shearing stresses as a function, this parabolic function, VQ over IT, where V is the shear, Q is the first moment of the area. You may need to brush up on that topic. I is the moment of inertia of the entire cross section, and T, or sometimes we'll use B, is the width of the section. We'll see how all that works. So we're going to learn how to calculate the shear stress anywhere in the section. In our next lecture, we'll learn how to calculate the shearing stresses in thin-walled sections. In today's lecture, we're going to be looking at the shearing stress as it changes from top to bottom of the beam. If you have a downward shear force or an upward shear force, how that shear stress varies from top to bottom. When we have a thin-walled shear section, then actually it's a little more complicated than that. And rather than just going top to bottom, we may have to work from all of our flanges through the member. That's what we'll learn about next lecture. But today's lecture not only will teach us about shear stresses in beams, we'll learn a little bit about shear flows in beams, and then the very important topic of being able to figure out using these same formulas how much shear will be in a fastener that's holding pieces together. Like if we nail a couple 2x4s together, what is the force in the nail? Or if we have an I section on an aircraft or a J section that somebody then goes and puts a strap and rivets a strap to the upper cap to beef the thing up. How do you calculate the force in that fastener? This lecture is the start of the theory and the fundamental approach that will allow us to calculate those forces accurately so we can evaluate those fasteners. It's a very important lecture. You'll use a lot in industry if you go into structures. Enjoy.
So to start off with, if you just imagine a 2x4, say a cantilever beam made of one single 2x4, and then you put a force. Imagine we have a beam, a cantilever beam, and let's say that it just is constructed of a single plank. For example, if we have a cantilever beam with a single plank, and if we put a load on the end, it is going to deflect like this, and its resistance to bending, if this is, let's call this T, then its resistance to bending is 1/12 BT cubed. That's the moment of inertia of the beam. Now if we have a beam, and let's say we put two of them on top of each other, and we also don't attach them together with that same point force, and each of these has a thickness T. Now our moment of inertia, if these are not attached, nothing attaching them, our I is now twice the moment of inertia because we have two 1/12 BT cubes. Now if we had instead glued these beams together or nailed them together, let's just say we've glued them together along here with a glue that can completely tie them together. Now you can see our moment of inertia is 1/12 B, and our total height is now 2t cubed. This means that our moment of inertia is 8 times 1/12 bt cubed. So if we compare these moments of inertia, the moment of inertia of the glued to the unglued beam, we see this term is going to cancel, and this term is going to cancel, and this term is going to cancel, and we're going to leave an 8/2, which means we have 4 times the stiffness. 4 times the stiffness. That means we deflect 1/4 of the amount. Why? Simply because we glued these together. Now if we had nailed them together, we can get the same effect, except now we're going to have to check, actually even with a bond we would check to make sure the bond is strong enough, and if we have nails we need to check that the nails are strong enough. We'll look at that in a little bit. The basic concept though is if we have a cantilever beam loaded with a transverse force, then by attaching those together we're going to get a much bigger moment of inertia. And what's going to happen is, if we clear this here, having two beams either acting separately or acting as one, we see this had 4 times the stiffness. Okay, now what that means is, as we're deflecting, because as we deflect, you can see what happens is, for these that aren't tied together, the deflected picture looks like this. You get the first beam doing this, and the second beam, since it's not attached together, it can slide along the first beam. It gets longer by a different amount, right? It's going to go into a different path, and it's going to end up having a different deflected picture. It slides between the two beams. If they were attached together, they can't slide, and they're forced to behave like this, where plane sections remain plane because it's attached all along here, so you can't get that slipping along this plane. That's develop shear stresses along there. We see the same thing if we had taken those two beams, not attaching them together, and if we had applied, say, a pure moment. Let's say we grab them at this end and apply a pure moment to them. Then that would allow the two beams to slide together without developing any shear stresses. But the shear introduces shearing stresses onto the beam. That's what we're going to be looking at today. So we see if we have a cantilever beam made of stacked beams, if we apply a pure moment, our strain distribution is linear. No sliding needs to occur because each beam is loaded up by the moment separately, and our beam remains shear free. There's no shear applied, and it doesn't develop any shear. But if we'd applied a transverse force, we're going to develop shear stresses between the planks. In this particular case, they're not attached, so they just slide on top of each other, and this beam is only going to have the moment of inertia of a single plank rather than of 4 planks tied together. If we had tied them together, they would have had a much higher stiffness, but then we would have developed shear forces. That's what we're going to look at. So our basic concepts, we can kind of understand this further if we look at a general section loaded in shear and bending. If we're loaded in shear and bending, we can then sum all of our forces on this. We can sum the forces in the X, Y, and Z directions, as we see on the left, sum of the force in the X, and we can write all of the shear forces in terms of stress. So we say, hey, this loading is going to cause stresses on every little point on this beam. If we focus on the little element, the little dA element here shown in the first figure, we see that the stress that it sees times the area that it's acting on is going to be the force. If we look at the force in that little member, the little stress times its increment of area, and then sum up all of those little elements along the face, we would get the total summation of forces, and since we applied no axial force to this beam, it should sum to 0 as shown in the first equation. If we do the same thing summing the force in the y direction, it better sum up to the force that we applied, which was v, and if we're saying up is positive, it should sum up to a negative v. If we sum all the force in the z direction, since we applied no z force, those should sum to 0. In the same way, if we take each of those stresses times their relative positions, then we can get the moment about the x-axis, the moment about the y-axis, and the moment about the z-axis. The moment about the x-axis is a torsion, and the other two are going to provide normal stresses. Now, our moment about the z, that's the only moment we applied, so that sums up to the actual moment. The other two moment summations better sum to 0 since we did not apply a torque and we did not apply a moment about the y. Now, if we pull out an incremental element out of this, we see on any little incremental element, we see that we have a shear stress and a normal stress. For example, we see on this face here, we have a normal stress shown here and a shear stress. This could be any little element like this one, which we've now blown up. And based on the definition of a shear element, remembering a shear element looks like this, and if we had had a force like this, we better have a force like that. If we have a force like this, as shown here, that's that one, we better have, because of these romantic little shear stresses, we better have corresponding stresses like this. This is the shear stress, this is the normal stress. Does that make sense? So what that means is, because this beam was, now if it had only been under the moment, we would have only developed the normal stress and no shear would have occurred. But because we applied a shear, that gave us a shear stress, and that shear stress, because they're so romantic and want to be head to head and tail to tail, that causes, while we have certainly a downward shear on the face, we're going to get a corresponding horizontal shear on the upper and lower surfaces of that incremental element. So this is how we develop shear stresses throughout the section. Now, before, when we covered shear stresses, we looked at direct shear, where our distance dx was so small that this force, we were pretending it just reacted here. We said actually that would cause a moment and the stress distribution is more complicated, but when we use P over A for this kind of stress, what we're really saying is that's just the average. Now we're going to be looking at how the stresses change from top to bottom of this section, and we're going to be doing a more rigorous approach for that. So if we consider a little prismatic beam like this one with a loading, you can see this is a simply supported beam with a loading, and we can see what the cross section looks like. And if we take a little increment of the beam, so let's go ahead and take this point C, create a new little cut just to the right of it, we'll call it D prime, and let's take that and let's pull it over to here. So what we're going to do here is take this a little piece of the beam right here, and we're going to blow it up right there, and we're going to study the forces on this face and the stresses. Okay, so when we do that, we find we can just put all the forces. Now this is a little confusing. The shear that's shown right here is really acting right down in here, and this shear is really acting right down here, but it's shown kind of higher than it actually is for whatever reasons in this text. So whatever we can see, since we made this cut where the distributed load is, that's shown on the beam. We have whatever stress distribution on each side of the cut and our shear stresses. We can now sum our forces in the x direction, as we see here, saying we're going to call positive to the right. Those better sum to 0. So we're going to get this stress times this little area. That's the change in stress there, right? The stress on this side minus the stress on the other side times a little increment of area. That's the area looking into the page, right? If we're looking at this section, that's this little area right here is what we're talking about. That area is what this is acting on. That's going to give us plus whatever. This is the only place we've got no cuts up here. This can't carry any shear force, so only down here, that H. So that's a little increment of force. We're calling that increment of force H, so that has units of pounds. That better sum to 0. We see that actually each of these stresses, this stress is just my over I, and this stress right here is just my over I. And if we now expand this equation, that we can write it in this form, which means the change in moment from one point to the other point divided by the moment of inertia times this quantity is equal to our shear force acting on this place. Now if you recall, this YdA is just our Q. It's the integral of YdA, right? That's the first moment of the area. The second moment of the area would be the integral of y squared dA, right? This is the first moment of the area. So the area times the y bar, and if you sum that up for all of those, so we're going to find that's key, and we can plug that value in for the shear. We just said that. Now if we remember, so we can now recalling that the change in moment is simply dm dx, right, times dx, the change in moment per unit x times dx, and that change in moment per unit x is simply v. We saw that last time. So we can actually write it this way. We can say the change in force on a transverse cut or a horizontal cut is just VQ over I times that little increment of distance ds. We can write that this way by pulling the dx to the other side, and we can introduce our shear flow. Now we've introduced running shear loads before, which we often call N S, or sometimes N of XY or something like that. But we said that when this is a running load, running shear, we often call it a shear flow, right? This term, and that's just that change in force per unit length. So what we see is we can write an equation for the shear flow given this equation right here. VQ over I. This is one of the key equations that we're going to use. The shear flow, which is a running load, pounds per inch, is equal to the transverse shear times the first moment of the area, Q over I. This is our cross section up here, and what that means is if we want the shear flow right here, we would need the Q on this piece. We'd calculate the Q of that. If we wanted the shear flow along this line, then we would need the shear flow, that we need the Q of everything above it, and so on. Okay, we're going to study out how this works. So the key to calculating the appropriate shear flow is to be able to tell what is the transverse shear at any point on the beam, on the point we're asking for, what is the moment of inertia of the full cross section, and what is the Q that is above or away from the neutral axis from the point where we want the shear flow. We'll study these concepts out more in detail as we move forward. So we saw on the last slide that the shear flow is just VQ over I, and this is used a lot in the aircraft industry. We're going to find that this is directly related to the stress. Remember, if you can think back to what we covered already when we were doing shear flows, if we know what the running load or the shear flow is, we know that the stress is just going to be that shear flow divided by the thickness. We're going to see the same thing is true. And we're going to use this relation to calculate the stresses acting and the forces acting on things that hold our beams together. So for example, if we have a composite beam like this, these three planks which are nailed together, We can calculate the force per nail by evaluating the shear flow at the intersection. We'll be looking at that in a bit. We can also use it for these kinds of problems. All of these involve a bonded or a nailed joint, which we can use the shear flow to calculate the loads. Here's another one and another one. All of these can be solved. Basically, what we will do is we will first calculate the I of each section, and we'll evaluate what is the shear force on each section. And then we will carefully evaluate what Q do we need to use to solve. For example, in this first one, we would find on each of these cross sections, we're going to need to know what's the shear acting on it. What's the shear acting on this? 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 The shear acting on this, the shear acting on this. We would compute the I of this cross section, the whole cross section, the I of this cross section, the I of this cross section, and so on. We would then go and say, well, where do we want the shear flow? Well, if we look at this beam, we say, well, we've got an upper plank and it's attached to this next plank by this nail. So if we want to know the force per nail, we're going to need to, moving from the centroid, which is somewhere about here, we were going to need to cut everything off away from the centroid through that plane. So if this is the centroid and this is the plane where we want to calculate our shear flow, we're going to cut everything on that's away from the centroidal axis, and we're going to calculate the Q of that, which is the area of that, 0.1 times 0.02, times the y bar of that, which is this distance right here to the middle of that segment. In the same way, if we wanted the shear flow in the nail down here, we would use this Q. That Q is just going to be 0.1 times 0.02, since we got to have this in meters, times this distance, which looks like it's 50 plus 10, 0.06. That's the Q that we would need to calculate the shear flow at each of these nails. We'd solve each of these other problems in a similar way. We can see these beams all have different moment of inertias. They may or may not have different shear forces, but each of them will have a different Q. Now if we look at these three examples, we see these, if this dimension is the same in all of these, then the same Q may apply, but because we have one nail here and two nails here and three nails here, that will give us a different shear flow. We'll study that out next lecture further. Now if we had made our section cut on a lower segment, remember last time we were investigating basically the same spot, but we were looking at the little element of beam up here. Now we're looking at the element just below it, and if we had done that, we would have gotten the exact same results, but in reverse. We would have found that delta shear is equal and opposite. The shear stress is simply that force, which is Q dx, divided by the area, which is T dx, which is just Q over T, shear flow over the thickness. This is what we've seen in the past. So we can write the shear flow this way. This is another common equation. What this means is we can write the shear flows as VQ over IT, like this, where T is that width dimension, equals VQ over IB. That's also very common. So basically what this T is, or the B is, it's really the width dimension where you want the shear flow. Often we'll call that T because it's off in the thickness direction, but it might be more accurate to often call it B because it's really the width direction. Okay? All right. What this figure shows is that the shear stress distribution is not constant. So while we may calculate the shear stress using this equation, and that's certainly true, that's the average shear stress on this space. The real shear stress distribution is going to be nonlinear like this. We're not going to do anything to account for that. We should just be aware that it's not a linear stress distribution, or not necessarily a linear stress distribution. And we'll notice that what that means is the shear stress up at the top, because our little shear element has to be 0 right here. So if we look at the little element right here, we know normally our shear element would look like this, but up here it's got to be 0 because that's a free face. But this is still our figure, so what that means is that this shear stress is going from 0 to something greater and greater, and then it's going to start diminishing, such that this always matches, these two match, but it's actually 0 here. We'll look at that further in the next slide. These equations do have limitations. They're not as accurate for cross sections that are short or flat. It will give you less accurate results where there's a sudden cross sectional change, and it won't work properly at a joint or inclined boundary. However, we're often going to blindly run forward and use it anyways, because the errors tend to be relatively small. Okay. So because we have our equation here, if we look at our shear stress distribution, remember we can calculate the shear flow at any point by just taking the Q of everything above it. So our basic equation is VQ over IB. If we want the shear flow right here, or our shear stress equals VQ over IB, where B is the width, right? You can see that the width, B, is the same from top to bottom for this segment. So if we know what the total shear force is on the section, V, and we know what the total I is of the section, 1/12 BH cubed, and we can see what the thickness is, which happens to be, or the width is, it's B everywhere. The only thing that's going to change as we work from our way from top to bottom is the Q. If we want the shear flow at the very upper surface, we'd say, well, the centroid is here, and if I draw a horizontal line at the point I want the shear flow, how much area do we have above that point? The area above that point is 0, therefore the Q, which is area times the y minus y bar, is also 0. If we want the shear flow right along this plane, we would take this area and it's y minus y bar. If we wanted the shear flow here, we would take this area and it's y minus y bar. And if we wanted the maximum shear flow, we would take this area and it's y minus y bar. That's what this shows. We see that this equation written out with calculus is going to give you a change in shear flow. Now it looks like all the little arrows are going down like this, but what happens is the magnitude is going from 0 at the top to some maximum value. Now our Q, remember, is A times Y, right? Our Y is from the centroidal axis moving upward. That's our Y dimension. Our Y is the dimension from here to the centroid of the piece. So if we look at the upper piece, if we look at remember the Q up here is 0, but if we take the next little strip, this Q is going to be small. It's going to be the area of that. If we go a little further down, this Q is going to be this area and this Y. This Q is going to be this area and this Y. And if we want the Q at the centroid of the CG, all these are the CG, then actually it's this area times this Y. You can see the area is larger, even though the Y is diminishing. The Y here is great. The Y here is, if we move down, we're getting a smaller and smaller Y, but we're getting a larger and larger area. So what happens is we're getting an increasing shear stress, but it's increasing by less and less as we get closer to the centroid. Then this Y term, because now we're down here, it's now going to be negative, so our Q goes negative. So now anything for the next segment, if we draw it over here, if we want the shear flow down here, you can say, well, actually I have all this positive Q plus this negative Q, so actually it starts to diminish until it gets back to 0. So the stress distribution in a rectangular section is parabolic, and we're going to tend to get a parabolic change in shear flow as we move from top to bottom. For an I-beam, we would have something that looks like this. So that concludes our conceptual lecture. I've got 2 more little sub-lectures for you, one on conceptual ideas and exercises, another for example problems. Just to recap, it behooves us to think about what we covered. We covered transverse shear on a cross section, which basically means if we have a section with a shear, we're going to need the V and the I and the width to get our shear stress, and we're going to need the Q, and that Q means that our stress distribution is going to build up in a parabolic fashion like this on a rectangular section with the maximum occurring right there. You'll notice the path that we're taking on this section and all segments we covered was top to bottom. Now we're going to look next lecture into when we have thin flange beams. We're no longer going to move from top to bottom. We're going to move from extreme fiber toward the centroid. So instead of moving top to bottom as we did in this particular case, we're going to move like this through the cross section. That's next lecture. But before we get here, we're going to stick with our top-down approach and we're going to need to study how this works out a little bit further in the next 2 sub-lectures that I have for you.